Now, let's see how a kick reacts and what pressures are involved when it's circulated out and allowed to expand. Circulating pressure is the pump pressure needed to overcome friction losses in the circulating system. This will include the pressure needed to pump through the drill pipe, drill collars, bit nozzles, and back up the annulus between the wall of the hole and the drill pipe. These friction losses vary with the viscosity and gel strength of the mud, the length and diameter of the surface piping, diameter of the drill pipe and drill collars, the size of the bit nozzles, and clearance between the drilled stem and wall of the hole. This diagram is an example of how the pressures are distributed and summed up for a total circulating pressure loss in a 10,000-foot hole. The total pressure needed to circulate the well starts at the pump, where static pressure is 0 and circulating pressure is 2,400 psi. This 2,400 psi pressure is used up in the circulating system by the 600 psi pressure loss through the drill stem, plus the 1,600 psi pressure loss through the bit nozzles, and the 200 psi pressure loss in the return annulus, for a total pressure loss of 2,400 psi. The 200 psi in the return annulus can be used effectively to raise the bottom hole pressure. For example, a 10-pound per gallon mud has a pressure gradient of 0.52 psi per foot, giving us a static bottom hole pressure of 5,200 psi in our 10,000-foot well. When circulation is started, the 200 psi pressure used to overcome the friction in the annulus is added to the static pressure to give us an effective bottom hole circulating pressure of 5,400 psi. This explains why some formation pressures are contained while drilling, but start to kick during a trip or when the pumps are shut down. It is desirable in any well control method to run the pump at reduced speed when circulating out a kick, to avoid excessive circulating pressures that could develop and exceed the pressure limitation of the pump or cause exposed formations to break down. At least once each day, the pump should be run at reduced speed, and the speed and circulating pressure written down for reference in case a kick develops. The pressure obtained from such a test procedure will be referred to hereafter as the pre-selected reduced circulating pressure. Now let's see what happens to the pressures during a test and how the data obtained can be used. First, let's consider the drill pipe and annulus as a U-tube, the drill pipe being the narrow leg and the annulus the wider passageway returning to the surface. A reduced circulating pressure of 1,000 psi, a 12-pound per gallon mud is assumed. It should be noted that most of this 1,000 psi circulating pressure, or 950 psi, is lost in the drill pipe and through the bit nozzles, and that about 50 psi is lost in the annulus. This loss in the annulus is, as stated before, additive to the 6,240 psi hydrostatic pressure of the mud column. Say that soon afterwards a kick develops and the well is closed in. The gauges on the drill pipe and casing are read, and it's found that the shut-in conditions are static with 260 psi on the drill pipe and 814 psi on the casing. Under this static shut-in condition, the bottom hole pressure and formation pressure are the same. The bottom hole pressure and consequently the formation pressure can be calculated. There is 10,000 feet of uncut 12-pound per gallon mud in the drill pipe, exerting a downward pressure of 6,240 psi. There is also a downward pressure of 260 psi on the drill pipe gauge. These two added together give 6,500 psi, the opposing bottom hole or formation pressure. Circulating out the kick commences with the pumps running at reduced speed, and the choke open to the correct amount to maintain the 814 psi that was on the casing when the well was shut in. The drill pipe pressure is now 1,260. The sum of the 260 psi, which showed on the drill pipe when the well was shut in, plus the 1,000 psi put out by the pump operating at reduced speed. Note the 50 psi bottom hole pressure increase due to circulation. Remember that when we first closed in the well, that we took gauge readings on the drill pipe and casing, then calculated the bottom hole formation pressure by adding the drill pipe pressure to the hydrostatic pressure applied by the uncut mud column in the drill pipe. We can now use this formation pressure information to calculate the mud weight needed to regain control of the well. The formula used to calculate the needed mud weight increase is 20 times the drill pipe pressure reading divided by the depth of the well in feet. The factor, 20, is actually 19.25, but 20 is used for convenience in doing a quick calculation. We plug into the formula our data obtained from the shut-in condition, the 260 psi drill pipe pressure reading, and the depth of the hole. Multiplying the top two numbers together, we get 5,200 over 10,000 ppg. Dividing the 10,000 into the 5,200, we come up with the weight increase needed, 0.52 pounds per gallon. Again, for convenience sake, we'll say 0.5 ppg. Then, by taking the initial mud weight, 12 pounds per gallon, and adding it to the required weight increase, we obtain 12.5 pounds per gallon, the mud weight needed to control the well. Up to this point, we've covered the causes of blowouts, what the indications of a blowout were, and how a kick would react, and what pressures were involved under certain conditions imposed upon it at the surface. Now, let's go through the actions, step by step, that the driller should take to kill a threatened blowout. At the first indication of a threatened blowout, and especially if there is an unaccounted for increase of the mud volume in the pits, there is no need to delay action. Stop the rotary table, pull up off bottom a few feet, and stop the pump. Immediately close the blowout preventer and shut in the well completely. Read and record the shut-in casing pressure. Read and record the shut-in drill pipe pressure. Read and record the pit level increase. By following these steps, the driller will immediately establish control of the well and minimize the entry of formation gas or fluid into the well bore, minimize the amount of mud displaced in the well bore, and permit determination of drill pipe and casing pressures. Stopping the rotary table, pulling off bottom a few feet, and shutting down the pump reduces the possibility of stuck pipe and permits a quick check to see if the well is unloading. If the well is flowing, the well should be closed in quickly to minimize fluid entry into the well bore, thus making it easier to control the kick. After closing in the well, the driller should wait a few minutes to allow pressures on the casing and drill pipe to reasonably stabilize. The closed-in casing pressure will be the initial back pressure to hold on the choke when circulation is started to kill the well. The shut-in drill pipe pressure is very significant. Without it, we cannot easily calculate the mud weight increase needed to kill the well. The shut-in casing pressure can be used to determine the mud weight needed to balance the formation pressure, but it's more involved because the fluids in the annulus are mixed. The barrels gained in the mud pit at the time the well is closed in will have a direct bearing on the pressure that will appear at the well head when shut in. If only a small gain is permitted, the shut-in casing pressure will be relatively low and the kick will be easier to control. If a large amount of mud is displaced by gas in the annulus, then the shut-in casing pressure will be considerable, even if there is only a small differential between the formation pressure and the hydrostatic pressure of the mud column in the drill pipe, and the kick will be harder to control. Once the well is shut in and the pressures on the drill pipe and casing are taken, there are 3 well kick control methods that can be used: the driller's method, the concurrent method, and the weight and weight method. All of these methods prevent further entry of formation fluids by holding a constant bottom hole pressure slightly higher than the formation pressure while circulating. All make use of the principle that the well must be closed in completely, and that pressures are read and recorded before subsequent operations commence. Because the driller's method of well kick control is the simplest system, is the most easily understood, and can be started without delay, it will be the method used in the following example of a well kick control. The driller's method of killing a well kick is accomplished in 2 circulations. On the first, the well is circulated under pressure, using the same weight of mud used when the kick was encountered, to remove the intruded gas or fluid. On the second, the well is circulated using mud of the required weight to balance the formation pressure and displace the lighter mud. The first circulation is started by opening up the casing choke and simultaneously bringing the pump up to the preselected reduced speed. The drill pipe pressure will increase too and is held constant at the figure obtained by adding the preselected circulating pressure to the recorded shut-in drill pipe pressure. The increased constant drill pipe pressure is maintained by adjusting the casing choke. When the choke is being adjusted, the driller must remember that there will be a time delay of approximately 1 second per 1,000 feet, measured down the annulus and back up the drill pipe, before the pressure increase or decrease appears on the drill pipe gauge. The time delay means that in our 10,000-foot well example, there would be at least 20 seconds after making a choke adjustment before a pressure change will show on the drill pipe gauge. Over-control resulting from not taking this delay into account has been the cause of many failures to handle a kick properly. For it must be remembered that the pumping rate must be maintained at a constant speed. However, the pump can be stopped and the well shut in again at any time without danger, so as to permit new observations of shut-in drill pipe and casing pressures. When the intruded fluid has been circulated from the well, clean mud will appear at the casing outlet, and pumping can be stopped if desired, and both casing and drill pipe can be closed in. If this is done, you should find that both drill pipe and casing pressures are identical. If not, continue circulating. As the kick is being circulated out, the crew prepares 1 or more pits of mud having the weight that was calculated to balance out the formation pressure. With the kick circulated out, the second circulation is begun using the heavier mud, and the same reduced pump speed as used previously. As the heavier mud is circulated down the drill pipe, the casing pressure is held constant at the last observed circulating casing pressure until all of the lighter mud in the drill pipe is displaced. Then the pressure control is moved back to the drill pipe until the heavier mud fills the annulus. When the heavier mud reaches the flow line, the drill pipe pressure should have reduced to the pre-selected circulating pressure, in this case 1,000 psi. Pumping can then be stopped, and well pressure should be 0 on the drill pipe and casing. If it's not, mud weight required to kill the well must be recalculated using the observed drill pipe shut-in pressure. The mud weight increased, and a second operation repeated. A worksheet containing all the necessary steps and instructions is important to the driller's method of kick control, in order to properly execute the operations with confidence, to eliminate wasted effort, and to ensure that successive steps are performed in the correct order. Use of a worksheet to kill a well may seem unnecessary, but the step-by-step procedures can be difficult to remember, especially when there are trying conditions, such as weather, stress, or other difficulties. As a summary of the driller's method of controlling a well kick, let's quickly review the well conditions and the sequence of pressures as the kick is circulated out and killed. Illustration A shows the situation immediately after the well is closed in. 12 pound per gallon mud is in the well. 260 psi appears on the drill pipe and 400 psi on the casing side after the pressures stabilize. Drill pipe pressure plus the hydrostatic head developed by the 10,000-foot column of mud in the drill pipe equals 6,500 psi, the formation pressure. The height of the intruded fluid in the annulus can be calculated, provided the pit volume gain was recorded, and the hole size is equal to bit size. When the pump is started and held at the pre-selected pumping rate to circulate out the kick, or at B, the drill pipe pressure will rise to 1,260 psi, the pre-selected 1,000 psi pump pressure, plus the 260 psi shut-in pressure, and be maintained there by adjusting the choke opening so as to hold a constant pressure on the formation. The casing pressure will rise from the initial 400 psi shut-in pressure to about 900 psi when the kick is pumped about halfway up the annulus. The 50 psi increase in the bottom hole pressure is the amount of reduced circulating pressure required to overcome the friction in the annulus. As pumping continues, the choke is continually adjusted to keep the 1,260 psi on the drill pipe, thus keeping the bottom hole pressure constant. 2, the gas is allowed to expand and the casing pressure to increase until the gas reaches the surface, at which time the maximum casing pressure, in this case 1,500 psi, appears, a figure well below the casing burst pressure. Finally, it will be noted that the mud in the pits will have returned to its original level when all of the gas is circulated out of the hole. When all of the gas is circulated out, as at D, the casing pressure will drop to 260 psi. The pressure needed to continue to maintain the 1,260 psi circulating pressure on the drill pipe. If the need arises, the pumping can be stopped and the choke closed, in which case the drill pipe and casing pressure should be the same, 260 psi. Now, the heavier 12.5 pound per gallon mud can be pumped down the drill pipe to displace the lighter mud, as at E. During this phase of the operation, the control is shifted to the casing, wherein the casing pressure is held constant at the last observed pressure reading, or 260 psi, by adjusting the choke. As soon as the drill pipe has become filled with the heavier mud, it will be found that the drill pipe pressure has been reduced to the pre-selected circulating pressure, or about 1,000 psi. Control is then shifted back to the drill pipe, wherein the drill pipe pressure is held constant at the reduced pressure by continued choke adjustment. When the heavier mud being circulated up the annulus reaches the surface, it will be found that the casing pressure has reduced to 0. The well will be dead. The blowout preventers can be opened. and the rig operation that was in progress when the kick was first detected can be resumed.